When we left off, we were talking about how to convert an ellipse in parametric form to Cartesian form, and we defined Cartesian form as just having an x and a y that depend on each other, as opposed to x and y both depending on a third variable t. So we're going to do that same thing with a hyperbola now. So we have x equals 5 secant t, y equals 3 tangent t. And just like we did in the first video, we're going to square both of these pieces, because in those Pythagorean trig identities, all of the trig functions are squared. So we need to square both sides first. So we'll get x squared equals 25 secant squared, and y squared equals 9 tangent squared. Then after that, we're going to divide by 25 and 9, divide by 25 on both sides, divide by 9 on both sides, because in the Pythagorean trig identities, the trig functions did not have a coefficient. It was just a coefficient of 1. So now we need to think about how can we combine these. So let's go back to those identities that we came up with the other day, or not the other day, in this previous video, whenever you watched it. So you may feel like you need to memorize these, and it's okay if you do, but if you don't want to memorize them, it's not too hard to just go back to right triangles. If this is theta, we can call this O, A, and H. And then we can apply the Pythagorean theorem, O squared plus A squared equals H squared. And then from this, we can derive these three identities by dividing by different letters. So for example, if we divide by O squared, that's going to give us 1 plus cotangent squared equals cosecant squared. So that's where this identity comes from dividing this by O. If you divide by A, you're going to get this one. If you divide by H, you're going to get this one. So you can always just go back to that. Now, which of these are we going to use for a hyperbola? Well, it's going to be the one that involves secant and tangent. So it's this one. But it's not currently in a good form that's going to allow us to totally convert this to Cartesian form. So we want to get it down to here. And how we do that is we're first going to add 1 to both sides. So we get tangent squared plus 1 equals secant squared. And then if we subtract our tangent squared over now we have secant squared minus tangent squared equals 1. So the goal was to get secant and tangent on the same side so that we can combine them, because now we can combine them, and since this is defined in terms of, I think, what do we got? In terms of x, and this is y, now we can replace these and get our Cartesian form. So we have 1 equals secant squared minus tangent squared. That is a true Pythagorean identity. And since secant squared we determined equals x squared plus over 25, and tangent squared equals y squared over 9, we can just plug those in here. And now we have our Cartesian form with just x and y. X squared over 25 minus y squared over 9 equals 1. Okay, so now what we can do is we can actually talk about how to sketch hyperbola precisely. So if x equals 5, then y is going to have to be 0. Similarly, if x equals negative 5, y is going to have to be 0. And that is because if I plug in x equals 5, I'm going to get 25 over 25 minus something, and that's going to be equal to 1. Well, 25 over 25 is already 1, so the only thing I can subtract would be 0. So if I want this to be 0, then y is going to have to be 0. So that means I have a point at 5, 0, and I also have a point at negative 5, 0. And I know that my hyperbola, because secant is x, is going to open horizontally. Okay, it's going to go boom, boom. Now, to really precisely sketch this, we're going to do this weird thing that's not going to make a ton of sense yet, but it's going to make more sense when we start talking about slope. So what we're going to do is we're going to go up to 3, 0. And let's actually draw in my tick marks here. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3. So I get this 3 because it's 3 squared over 9 would be 1. So I'm going to go up 1, 2, 3 and just make a little mark. It's not a point. I'm just marking that point and then mark here. Okay, I'm going to use these to make a little box. This is not part of my graph. This is just going to help me sketch my graph. Okay, and then using that box, I'm now going to draw diagonals through the corners of the box. And these are going to serve as my asymptotes for my hyperbola. So my hyperbola is going to asymptotically approach these values. And we will talk more about the reasoning behind where these boxes come from, but for now we're just going to accept this process. So now from 5, 0, we're just going to extend out. Let's make this the same color. So extend out and approach these asymptotes. And there's the sketch of our hyperbola. Okay, so let's do another one. Convert this to Cartesian form. So we get that y squared, we square both sides and then divide the 49, divide the 4 over. And then we need to combine these. Remember that our Pythagorean trig identity is secant squared minus tangent squared equals 1. So secant's always going to come first. So in this case, secant squared is y squared over 49, so that goes here, minus tangent squared equals 1. Okay? So now let's think about how to sketch this. Just like before, when y equals 7, x is going to have to be 0. When y equals negative 7, x is going to have to be 0. So here we go. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. There's our points at 0, 7 and 0, negative 7. Okay. Now to make our box, we're going to go over how many? We're going to go over 2. Okay, so 1, 2, 1, 2. So, and we're just going to make a little mark here. It's not a point. It's just going to help us draw that box like we did before. So now we can draw a little box from here. And then we can draw our asymptotes that are going to go through the two corners of the box. Okay. So then what we have is we have a hyperbola that is coming from these points and it's going to approach those asymptotes. So to get full credit on a question like this, you just have to make sure that it starts at the right places and that you have the asymptotes drawn in correctly. Okay. So again, we will continue to talk more about where these asymptotes are really coming from and what is going on as the hyperbolas approach them. But for now, you can just accept the process of, well, it starts at 0, 7, and then we're going to go over 2 because this is 2 squared, 2 to the left, 2 to the right. Okay. Oh, so yeah, this is where, and you know what, I'm just going to go ahead and do this one more time. At this point, if you want to just skip to the closure, you can. But I'm just going to do this one more time just to make it clear. So, to try to make it more clear. So again, when y is 7, x is going to have to be 0. Because that's the only way this equation is going to be true. And same if y is negative 7. So when we sketch this, we're going to go up 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, and then, so that's 7, right? Up 7, down 7. Secant goes from 1 to infinity, so we're going to go 7 to infinity and negative 7 to negative infinity. Okay, now in front of tangent we have 2. That determines the other part of this weird box thing we're using to more precisely sketch these hyperbola. Okay, so from there we're just going to make this box. And then that box, the corners are going to help us come up with our asymptotes. Our asymptotes that are going through those two corners. So now when we sketch this hyperbola, we just need to make sure that we're coming from the right place and that we approach those asymptotes. Okay, so we're coming from here and we approach those asymptotes. Okay, cool. There's your graph. Okay, so here's your closure, and you're going to submit pictures of your closure to Google Classroom by 5 p.m. on Friday. So you have to convert this ellipse to Cartesian form and then sketch it, and then convert this to Cartesian form and then sketch it. Take a picture, submit on Classroom, and you now can work on more of your problem set. Make sure you keep working on that, working through it. As we finish each lesson, there's more problems that you can do.